All right, so on page 7, let's go over these answers real quick. It says we got a block being pushed up at a constant speed up a ramp from point A at the bottom to point B at the top. And we know that from the picture. The direction of the force on the block by the hand is horizontal, or it's parallel to the ramp. There is friction between the block and the ramp. And so we got friction. We got an applied force by the hand, and it says the distance between A and B, 1 meter. Just keeping it nice if you wanted to do any, work on it. The work done is what all the questions start with, but look at the by. And so A is the work done on the block by the hand. B is by the normal force. C is by the frictional force. And then D is by the gravitational force. Well, maybe a good place to start is with drawing what? Force diagram. And so on the block, during its ascent up the ramp, we've got gravity as always, right? And then what else? They mentioned normal. What direction is our normal force? Perpendicular to the surface. And then we've got the applied force. The hand is pushing it. What direction? Up the ramp. And then friction, they mention, is probably down the ramp, that resistive. Everybody good there? And so this question, we're not calculating. It's just, is it 0? Is it positive? Is it negative? Or can't be determined? And so first, what about the hand? What kind of work is the hand doing, the applied force? Positive. How do we know? Right. And so remember the applied force is the same direction as the distance traveled, A to B, not B to A. That would be a different answer. And so work by any of the forces has to be parallel. So the emphasis on this one is about parallel. And so since they are the same direction, or you could go with that cosine theta, what's the theta separating up the ramp, up the ramp? What angle separates? Because in this equation, that angle is not the ramp angle, it's that separation between your force and distance. And so up the ramp has what angle separation? 0. And so cosine 0, either way you look at it, you should end up with a positive answer, okay? What about the normal force? It's 0, why? It's not parallel at all, okay? So Fn is not parallel to the distance traveled, right? Actually, they would be perpendicular when you draw it out, because by definition, Fn has to be perpendicular to the surface that it's moving on. Or cosine 90 should get you the mathematical answer of 0. What about the frictional force? It'll be negative. You've caught on, right? Hopefully how to figure out. I'll go on and just draw them here. Or you could cosine 180. It's going to be negative work. And what about the gravitational force? Negative. Wait, does gravity, is it parallel? Right. So if you were to draw out, as we wrote it on the diagram so far, gravitational force straight down, but it's moving straight up. Now don't try and do the angle between them because it's not equal to the ramp angle, but I would say don't use this one. Use that component of FG parallel trying to bring it down the ramp. Okay, so take that component approach. And so the work done by gravity is the parallel component of gravitational force times distance. And if you draw it out the way I have, gravity should be doing, what kind of work is gravity doing? Negative. It's trying to pull it down, but the object's going up. Well, just for fun, let's add a part E. There is a type of work that hasn't been asked yet by this question, and I'll just put it at the top, since OneNote took me to the top. What is the net work done on the object? 0. Why? Key phrase there, constant speed. And so if it has a constant speed, then tell me about the change in kinetic energy using the work energy theorem. Net work is equal to your change in kinetic energy. Your change in kinetic energy would be 0, right? That final minus initial, 1/2 mv squared minus the exact same 1/2 mv squared, there is no change. And so you'd have no net work. And that should also agree with what we studied in the fall. What would the net force be on the object?
0.
It'd be 0 because the F net equals ma. What's your acceleration at constant speed?
0.
It's 0. So all the things we said in the past should align with what we're doing in the present. Good deal? Okay, I know it's jumping around a little bit, but I said we got just a little bit more notes, 10 minutes maybe max, and then we'll dive back into the practice, okay? And so go on and click or turn to page 13. We have another blank piece of paper. We'll look at power, and then I'll add maybe on the second half, we'll talk about graphs. Page 13. Top half power, second half graphs. And so what is power as it relates to work and energy? And so power, and I believe this equation is on the formula chart, power is when we change that energy, it's the rate at which energy changes. And so for a definition, rate at which energy changes. Or we learned last time that when energy changes, work is being done. So you could define it as the rate at which work is done on an object. Okay, and right now we would probably be looking at the network and the changes in kinetic energy. Later, when we learn about potential energy, maybe it's potential energy that's changing, okay? And so key word here in both ways, in both definitions, is rate. What does it mean to have a rate of something? The rate at which an object moves, the rate at which the speed changes, the rate at which work is done. Rate tells us what? What are we measuring? Per second. So it's got time involved. The rate at which I clap. I can do a slow clap or a quick clap, right? And so it's power equals that change in energy over time. Maybe it's a delta time. Time is, you can look at the time interval or you can look at the time elapsed. And so delta T, I don't know what the formula chart has. Same though. Or applying the work energy theorem, it can be that work divided by time. Let's talk units. And so units of power, well, the unit for energy and work, do you remember the new unit? Joules per, what's our SI unit for time? Seconds. We may not daily speak in terms of seconds, so maybe the problem will give you hour or minute, okay? You got to convert it to seconds. Joules per second, both of those are SI, this is acceptable. However, it's equivalent to another SI unit for power. Anyone want to take a guess? You've heard it before. Not volt. They still have electricity ones on there. watts. Wait, what? Wait, work, what? I get that joke once a year. Okay. Again, capital W. Formula chart says it's work when it's in equation form, but as a unit, it stands for watts. In forces on a force diagram, it could represent weight. So be careful of the capital W. It could have 3 different contextual meanings. So if it's out beside a number like a light bulb, right? A 60 W light bulb, is that 60 weight, 60 work, or 60 watts? It's 60 watts, okay? And so the wattage on a light bulb is telling you how powerful it is. It's telling you how effective it is at changing the electrical energy to light per second. And that should make sense. If you've never tested different light bulbs, the higher the wattage, what can you say about the light it gives off? Brighter, because it has more energy in that same given time, right? And we don't typically time them, but you know, time is life, a second, a second, a second. Does this make sense? So it's really not hard. It's just that division, right? I can change my energy. I can speed something up slowly or quickly. It depends on the power. And so a lot of times the problems that we'll look at, we use motors to move things, right? Now, I don't want to talk about lifting because that's potential energy, but if I had something, you know, on the other side of the room and maybe I have a motor gizmo and I, you know, get a rope attached to it, the motor, if it's real powerful, can bring it to me quickly or it can bring it to me slowly, right? So motors are an example of how we can have power. Light bulbs are an example of power. Here's another one. In the same spirit of units, there's a common unit, and it does pop up on the AP exam. KW, and that's a lowercase k, capital W, lowercase h. What is this? Oh, I heard someone say per. Do I see division? No. Not pico. What? Okay. Pico? Okay. Do y'all ever wonder why nanopod? I don't even know. Are nanopods even a thing anymore? Isn't that the MP3 player that Apple came out with a few years ago? Nanopod? iPod Nano? I always said, well, why not come out with a picopod? It's funner to say. It'd be smaller. Anyway, they didn't, you know. So KWH, kilo is an SI unit prefix. Watt is the unit for? Power is what the unit, the variable is. And then hour, and it's a times hour, that's a unit of time. Now it's not SI, but kilowatt hour, maybe you've never heard of this, but if you go home tonight and say, Mom, Dad, can I see the electric bill? Somewhere in there, you're charged a certain number of cents. And it's been a few years since I've looked, but you know, 17 or 20, we'll make it nice, 20 cents per kilowatt hour. What does the electric company charge you for? Do they care what kind of light bulbs you use? What is this a unit of? Kilowatt hour. I got power times time. What is kilowatt hour a unit of? No. Okay, work and energy. And so it's actually work or a change in energy. This is a unit of energy. And I'm pointing it out because, again, I'm going to highlight energy. AP is all about unit equivalence. Kilowatt hour is a common everyday unit. The power company or electric company doesn't care what kind of light bulbs we use, or they could care less if I keep my lights on all night, right? I mean, overall, you could say, oh yeah, more money for them. What are they charging you for? 20 cents per kilowatt hour. They're charging for how much energy they have to transfer from the power station to your house. Now, can we say, oh, I regret using that energy, I'm going to send it back? Once you use that energy, it's used. You can't send it back, right? And so whether it's the stove, the cell phone charger, or a light bulb, this energy that we use from the power company is in kilowatt hour. And you're like, why not just keep with SI? Let's convert kilowatt hour, right? Kilowatt times hour. Let's stick with 1. I got to start with some kind of number. So 1 kilowatt hour. How many joules would that be? Well, we can convert the watts. No, let's convert to watts. Kilowatt to watts. And so the kilowatt on bottom, watts on top. 1 kilowatt is how many watts? 1,000. Kilo is 10 to the third. That's on the formula chart, or it's 1,000. And so kilowatt goes away. Now we're at watt hours. Let's get it to seconds. And so 1 hour, now we could go to minutes. So there's 60 minutes in 1 hour, 60 seconds in 1 minute. How many seconds are in 1 hour? 3,600. And so now we would be in watt seconds, which would be comparable to a joule. Everybody's SI there. But what's the number? Whatever 10 to the third times 3,600, it would be 3.6 times 10 to the sixth. Can you imagine the everyday consumer getting a bill with numbers in the millions? They'd freak out, right? And so again, we don't go around reporting our age in seconds. We report it in years. It's a simpler unit, okay? So we don't have crazy numbers. So that's why, I'm guessing, I mean, there could be other reasons, but they don't want their consumers seeing all those zeros in a gotcha kind of way. Questions on power? Just the rate at which work is done, the rate at which energy is changed. And right now we're focusing on kinetic energy. By the way, I talked about electric company. We don't do electricity anymore. So just that's a fun daily fact. Don't worry about electrical energy. You would see problems with kinetic energy. Like I said, that motor to move an object, okay? Okay, let's take a look at graphs. And so graphs, I mean, we're still dealing with boxes moving. All the graphs from the fall are still up for grabs. Position graphs, velocity graphs, acceleration graphs, force graphs, all that was typically versus time. A new type of graph to get familiar with, okay? And there's at least one question I remember in this packet that has it, is a force distance graph. So what if I'm able to plot the force exerted on a box and I know the distance it travels? We'll start nice. We'll say it's a constant force, right? And so maybe here. And so it's not about the numbers here, it's about the concepts. Well, we know that work is equal to force times distance. How can you find work from a force distance graph? Area, you know, we need to multiply that force times distance, that base and height, right? Base times height, height times base, same difference. And so it's the area that gets us work. If it's a constant force, we get to see a square. What if it's a changing force? Maybe, yeah, some kind of variation of a triangle, okay? 1/2 base times height. Or you could even see something like so, right? And again, real life has curves, but you're not going to have to do area with integral in calculus, at least for this course. You would estimate to the nearest triangle or square. But area. Now, typically, we've done slope. What would slope give us? Don't say number like 0, so go to one of the lower ones that actually has a slope. Yeah, there's positive, negative, but what's the physics behind the slope? It would be a change in force divided by a change in distance. Is that going to give us work or energy? It's not work. And I hope you're struggling because we haven't talked about it yet. Next week, we'll learn that this is something. So I'll say later, the slope, and I'm going to say can, depends on the problem, equal something called a spring constant. So that's the future. That's a little tease for next week. When we start talking about springs, every spring has something that we call a spring constant or force constant, some textbooks call. And so it's how many newtons per meter. But if the problem doesn't even have springs in it, like some of ours that we're seeing this week, well, you're not going to have a spring constant for a non-existent spring, right? So it's isolated to spring examples. So don't worry about slope right now. Area tells you how much work is being done on the object. And maybe it's a net work, maybe it's an applied force. Depends what kind of force is plotted, okay? If it's a frictional force, that would be the work done by the frictional force. That's it. Questions on our little notes today? Okay. Well, let's go back to page 3. We'll pick up where we left off last time. It looks like we had that box that was being pushed at a 45-degree angle above the horizontal. I think we did part A, yes, or I gave y'all time and then we worked it. And so we got that the work done by the applied force was 21 joules. And again, you could do the angle between the force and distance, or you can find the component of the force that's parallel to the distance. It's the same math, but like 2 different approaches. And then work done by friction. It looks like we tried to use the same FD cosine theta, but we ran into a problem. Uh-oh, we don't know mu just yet. Hint, hint, part C wants us to find the mu. And so how else do you find the work done by friction? Well, it doesn't really tell you in the problem to do this, but don't forget, if you have multiple forces doing work on an object, they can be put together for net work. And so that's the approach we took for part B. And so, yeah, this is the answer to part B. I know I bled over. Y'all know me by now, right? Sorry, I write big. And so the answer for part B, we found by doing a change in kinetic energy. They gave us mass. They told us something about the final velocity or speed. We had to assume it started from rest. And so we did that change in kinetic energy, used the work applied, and we got an answer for the work done by friction. Now, question came up yesterday, is my answer negative or should we put a negative in the statement above? And honestly, it's tomato, tomato, as long as you just do the negative once, right? If you get an answer that's negative, don't say, oh, I need a negative, negative. And so, because some people, if you watch this, some people put the negative in the problem and they got a positive answer. As long as there's one negative. An AP, on the AP exam, they usually take care of this issue. The question will say, determine the magnitude of the work done by friction, okay? because the magnitude of the work by friction is just like the absolute value. They just want to know how many joules, right? Okay, everybody good, A and B. Part C. Now we know the work done by friction. They want the mu, the coefficient of kinetic friction. So how are we going to solve for it? Mu Fn. So the part that didn't work earlier, we can bring down. And so don't just think force. We just found the work. So I'm going to use the work of friction equals the force of friction times the distance. And then it looks like we had tried the cosine theta, so I'll just bring it down. Remember, that's the angle between the force of friction and the distance. It's not, don't start thinking, oh, they said 45 degrees. Every force is 45 degrees. No. That's why diagrams help. And so we know the work of friction is that negative 896 joules. Force of friction, we don't know, and you can either solve for that, or we know it's equal to that mu k times Fn. D, the distance it travels, the distance that friction acts on the box is 15, they set up above. And so 15 is the distance. And then we get this cosine. And I'm going to scroll to the diagram. Friction acts to the left. The box moves to the right. What angle separates that force of friction and the distance traveled? 180. Now, if you just tell yourself, oh yeah, it's negative, I get it. But when you actually plug it in, 180, cosine 180 is -1. That's how the negative is going to take care of itself. And so one more number to plug in before we solve for mu. Basically, at this point, we would have it solve for frictional force. Fn is equal to what? The weight? There we go. And so here, we have not dealt with normal force yet. But hopefully you recognize that it's not equal, at normal force is not balancing the weight because I have that additional lift. We drew our normal force smaller because we're lifting it off the ground. The ground doesn't have to push as much. And so you can start with the two ups are going to balance the one down, kind of a balance statement, and then solve for Fn. Fg minus Fay. And so we haven't done this at all yet in this problem. We need to go solve for it. Fg, what do I plug in? Mg, the mass times gravity, and we'll go with 10. Moral of the story, don't just say 10, because that's the number one mistake students make. They're like, Fg, oh yeah, 9.8, 10. It's mass times 9.8. And so the mass is given in the problem 50 kilograms. And so 50 times 10, this is mg, minus Fay, I don't have it on my diagram yet, but when you draw that component in, hopefully you see its opposite theta, and this is the angle of the pull, not the angle separating anything, not 90 degrees, not 180, not 0. This is the actual 45 degrees to find the force. And we'll use what function? Sine. And so Fa, is this the 200 number? Yeah. And so it'd be the 200 times sine 45. So this is Fa sine theta. And make sure your calculator's in degree mode, punch it out. Let me know what you get. Sorry. Okay. We all get that? Just as a double check. I don't remember what it should be.
Oh, 200.
Oh, okay. So now 500 minus that number So that one was 141. 300 and,
58.5.
yeah. Wait, I said 358?
58.5.
50.5. Okay, so 51, we'll just round it. So we get a normal force, 351-ish. 58. Oh, it should be 59. Okay, I thought I'd heard it 8, but I don't know what it is about me that when people start spelling out or listing out numbers really fast, I'm like, whoa, whoa, whoa. I don't know if it's the auditory visual learner difference in me. Anyway, I've always struggled with it. And don't spell a word fast because I get lost. Okay, 359 is our normal force, so we can go in and plug that in. So I'm just going to erase, running out of room. I'll just put it there. Moral of the story, negative should go away. Do the algebra, let me know. And as you calculate it, maybe those not calculating, what's the expected answer for our coefficients of friction? Less than 1. So we should get an answer less than 1. If you didn't, it'd be a red flag. Hey, wait. Maybe you forgot the distance. If you forgot the distance, and usually coefficients 2 decimal places. And so hopefully you get something point. So round to 2 decimals, what do we get? 0.17?
Yeah, pretty much.
Pretty much, oops. 0.17. Unit? None, because coefficients at the end of the day are in Newton over Newton, and that's no units are left. So there's our answer to point C, part C. Good? Is it all coming back to you now? We did some old stuff there, a little bit of new. Okay, D. What would the final velocity, what would the final speed be if the angle was 45 degrees below the horizontal? So now, instead of lifting it up off the ground, we're pushing it into the ground. Hopefully this sounds familiar. This is what we did on the prior page last class. So y'all don't have to flip there, but on page 2, at the bottom, we use the concepts of work kinetic energy theorem, so that when you push down on the object, what happens to your normal force? Increases. What happens to the frictional force? Increases. What's going to happen to your change in kinetic energy and speed? It's going to decrease because you're subtracting a bigger work of friction. And so we did the concepts on page 2. Now we're going to do the math on page 3. And so that's a tiny space to work. So I'm sorry, I'm going to slide over here. And so how is it all going to change? Well, I'll do a quick diagram. Now we're pushing down, and that's the biggest difference. And so that y component is the same direction. So we know from page 2, it should be a smaller speed than 7. Let's calculate it, see if we get it. And so we got to look at that net work equals change in KE, kinetic energy. And so that's final minus initial kinetic energy. We can still assume that we're starting from rest. And so kinetic energy final is that 1/2 mass times the final speed squared. And that's what we're solving for, VF. So what about the net work? Well, are we still gonna have applied work? We're still pushing on it. It's still gonna move in the horizontal. Did any change happen with the horizontal applied force? No. So the same horizontal component, so WA is the same. So later, 21, 21. And we said friction did negative work. And so the work of friction, is that going to be different? Yeah, so we probably need to go find, now we know the coefficient, right? The only difference is normal force. And so the numbers are going to be nice. So our new normal force is Fg plus Fay. And so we know the weight is still 500. Fay is still going to be the same number, that 141 number. Is that right? Okay. I'll just forget the decimals for simplicity. And so now the normal force, instead of being 300 something, it's 641. And so now to find the work of friction, we can say it's the frictional force times the distance times cosine theta. And then the frictional force is that mu Fn. And just keep it going. We know the coefficient is 0.17. That would be the same because they didn't change the type of surface. But now the normal force is 641. Oops. Distance, same 15. Cosine, well, actually, here's where I talk about don't double negative. If I say cosine 180, it's going to come out negative, yes? But I already said friction did negative work. So you don't want to double negative, right? And so to correct this, I can either make the negative there a positive or just, we already know it's going to be. We already know it's going to come out negative. You don't want to end up double negative, okay? You should not add, because then you'd actually get a velocity or speed greater than 7, red flag. So I'm just going to leave that part off. And then the mass is 50. So now, do the math. Last step would be square root. And if you get a sub number, that work done by friction should be bigger than 896. So if you do just work of friction there, it should be greater than 896. Oh, I meant just the work of friction, just that part. Okay. But the answer you got is less than 7, which should be because that's a smaller speed compared to the original. Which what'd you get? 4.4, which is less than 7 meters per second, which is good. More friction, it should slow down. Less than 7. Did everybody else get 4.4-ish? Yeah, okay. Okay, let's keep the practice going. On number 5, a bullet mass is 20 grams. Grams. Convert to kilograms, okay? So bullets are really small, so, you know, small mass, you don't want to report that as point something, but we want to convert to kilograms. And so how many kilograms, how many decimals do we move it? 3, so 1, 2, 3, it'd be 0.02. It's fired at a velocity, a launch initial velocity or speed of 200 meters per second. Small objects can go fast, right? And it's going to go through a 2 centimeter block of wood, centimeter. Got to be meters, so convert your centimeters to meters. Centi is how many decimal places? 2, so I got to move it 2 to the left, actually, yeah. So centimeter, think of your ruler or meter stick. It's 1 meter. It's got 100 centimeters. They're small. And so 0.02. Now, I personally don't like that 0.02 kilograms, 0.02 centimeters. So I'm going to be, when I plug them into our equation, I am going to use the units there just to make sure you know, it's not always the same. You got to make sure you plug the right thing into the right place. And then it says if it exits at 60 meters per second, exit, this is our final speed, determine the average force exerted by the wood on the bullet. Now, why does it say average? So a little concept here, because it's not the last time we'll see average force. The graph, D or time, it would be the same. The graph of this block of wood exerted on the bullet would be something like this. As it enters the wood, it's very little contact, very little force, right? And then it goes all the way through the wood, and as it exits, very little contact with the bullet, okay? And so that's why it says the average force. Now, we're not going to do any different math. In our network statement, we'll just look at it as a net average force, okay? So don't get caught up on the average. Okay. So what did they give us? They gave us mass, a couple speeds. They gave us the distance that it slows the bullet down. Determine the average force. And so how do I connect all this? As it goes through the wood, it's just the work done by the wood, or you could call that an applied work, which it's friction, right? It's slowing it down. So you could actually here say it's going to be negative. The wood is slowing the bullet down. And the work energy theorem says that the net work done by the wood is going to change the KE. And here nobody zeroes out. So final kinetic energy minus the initial kinetic energy. And I'm going to do something different on this one just to show you it's a possibility. And so the wood's going to exert a force over a certain distance. And so we can say that average force times distance equals that 1/2 mv final squared minus 1/2 mv initial squared. So what I'm going to do different isn't going to change the physics. It's just kind of how you approach the mass. The mass of the bullet doesn't change. We'll ignore any deformation or losses, right? And so I could factor out the 1/2 mass. Now I want to emphasize what remains. Do you take the difference in the velocities and then square, or do you square and then take the difference? Square and take the difference and do the math both ways. It is different, okay? But you want to square and then subtract. And so the speed's given. It initially is 200 and exits at 60. And you'll notice it is going to be a small number. That's okay. You have a slowdown. You need a negative change in kinetic energy. And then the mass, 0.02. And that's kilogram, just to make sure. Distance is also 0.02. But just to be clear, that's meters. The nice part about 0.02, 0.02, and the way centi and kilo worked out, I got 0.02 on both sides mathematically. So what's going to happen? You can actually cancel out. And then 600 squared, 60 squared is 3,600 minus, and 200 squared would be 40,000. So it's okay, don't forget your half. And when you do that subtraction, the negative should go away. What do we get? And it's okay if it's a big number. We want to slow down that high-speed bullet, right? Yeah. 18,200 newtons. Now that's an average. So if it starts at 0, right? It's 18's the average. It's going to go higher at its maximum point. And so you could actually solve for the maximum force by doing a mathematical average, right? Initial plus final divided by 2. But it wouldn't necessarily be 100% because in real life, is it going to change force uniformly like that? No, a real force time distance graph there would have curvature to it. Questions on this one? It might sound a little different, but look, we did the exact same physics. Work energy theorem. Number 6, what about a coffee filter with a mass? They've already converted for us, 0.005 kilograms. It's dropped from a height of 5 meters, and it reaches the ground at a velocity or speed of 2 meters per second. Now, if it's dropped, what can we assume the initial speed is? 0. Determine the work done by the drag force. Drag, AKA air resistance. So here it's kind of that parachute coffee filter type. And so this is our air resistance. Now don't just say, oh, we always ignore it at 0, neglect it, right? Here we're specifically being told not to neglect it. But so, coffee filter, I'm not the best artist, kind of looks like a crown, I don't know, whatever. What forces are acting on the coffee filter when you drop it? Huh? Yeah, we don't neglect the air now. Gravity is going to pull it down. And as it falls down, the drag, air resistance, is going to act what direction? Up. How big do I draw it? Small compared to the weight, right? It's still going to accelerate and speed up in the downward direction. And so that upward force has to be smaller. So call it F air, drag, it's same. And that's it, right? As it falls through the air, that's it. My hand is no longer in contact with it. No one else is either. And so each of these has the potential to do work. And so net work is the work done by gravity plus the work done by air. Hopefully you see both are going to do work. It's moving in the downward direction. And so gravity is going to do what kind of work? Positive. Drag will do negative work. So right there, I've already done the negative. So we'll be solving for a magnitude value, right? If I left everybody positive, you'd get a negative answer. So as long as the negative is only done once. Well, before we take that further, net work is also equal to that change in KE, final minus initial, which we said it starts at 0 initial speed. So what's the initial kinetic energy? 0. And so my next line, work done by gravity minus the work done by, I said air, drag, same thing, equals the 1/2 mv final squared. To solve for air, we can subtract the work done by gravity. And one more thing before numbers, what can we plug in for the work done by gravity? Work is equal to, force times distance, so the force of gravity times the distance. Now, I'm not going to include the cosine theta. We already said it's doing positive work, right? Correct? And Fg is mg. So you could then say mgd. And so now let's plug in some numbers. 1/2 the mass, and it was super duper small. That's okay. And the velocity or speed, did they say it was 2? 2. Don't forget to square. Oh, mass again. Does mass cancel? No, it's not on the left-hand side, right? And then gravity, we'll use 10. The distance, how far does it fall? 5 meters. And so go on and work it out. You can half the 2 squared, right? Half of 4. What do we get? And the negative went away, yes? Yeah, it should have canceled out because we're solving for the magnitude of the air. So 0.264, what's the SI unit for work? Joules. Good on that one? Okay. Now, just for time's sake, I am going to skip this next one. You can still, try it during independent practice sometime. There's another ramp one on here that's a little more complicated. This one's easy. Surface is smooth. Let's do one where it's not smooth. I think it's on page 4. Fun with freshmen. So that's going to be, I know. I didn't write this, but this is all in fun. Nobody gets hurt in physics land. There's no bullying or anything going on, right? Everything's nice on paper. So we'll do this one and go back up and do that other one. Assuming we get some ice and snow some Friday, you put a 100 kilogram freshman, or it could be brother, it could be sister, it could be friend. You're not trying to hurt them, in a trash can. Maybe it's not full of trash. And they release them from rest. So initial velocity is 0. So he slides down a 15-degree slope. Careful, it's not 15 meters. It's a 15-degree slope. So it's an icy slope. It's a hill, right? And so maybe we draw that here. So here's our, barrel with our freshman or person in it, whatever. It's a box. You slide a box down a ramp and it's 15 degrees elevated. Assume no friction between the ice and the smooth barrel. Okay, so we've slicked it up, no friction. Starting from rest, how fast will he be going after sliding 4 meters? Ms. Earhart, this sounds like old stuff. This sounds like kinematics and forces and true story. Yes, you can solve it that way, but let's try solving it the new way. So force diagram, what forces are acting on the person, the object? We got gravity, we got normal, and we're just allowing them to slide down. We're not pushing. And right now it's smooth, no friction. So this is it. Who's doing work on the object? Just gravity. And true story, is it all a gravity? It's just that parallel component of gravity. So I'm just noting to self, I better use the parallel component. And so hopefully you remember to do your triangle. And we reviewed ramps the other day. So FG parallel is that mg times what function? Sine theta. Now that's the ramp angle. It's not the angle between your force and distance. And is gravity going to be doing positive or negative work on our person? Positive. So it's a positive work. And again, net work is equal to a change in kinetic energy. I'm going to go on with final minus initial. Just I'm running out of room already. And if you start from rest, initial 0. Gosh, this is exactly the same. Well, pretty same feeling as last couple questions, yes? Okay, so nothing new. And so the FG parallel times the distance, and then cosine theta if you want. We've already said it's positive, so I can erase that actually. Equals that 1/2 mv final squared. Mg sine theta times d equals 1/2 mv final squared. What do you notice about mass? It actually will cancel here, okay? We're not solving for work, we're not solving for energy. So if you want, now they did give it to us. We know it's 100 kilograms, so keep it if it makes you feel better. But if you take everything to the terms, the simplest terms for what you're solving for, you'll notice mass cancels. And so we're solving for VF, and so VF would equal, I'll keep it squared. I'm going to multiply both sides. And then you take the square root. So 2 times 10 times sine 15 degrees times the distance, and it tells us 4 meters in the question. Again, if you were a rebel and did kinematics and forces, you'd have to find the acceleration with forces and then use kinematics to find the final speed. Okay, you should get the same answer. Because we said that the force component of gravity that's parallel to the surface, FG parallel, is the same direction as your distance traveled. And so you can take, using that equation, it's not always necessarily the easiest thing to do angle between them. That would actually be more of a challenge here. And so I would say, okay, if I can't figure that out nicely, use the component of the gravitational force that is parallel to the distance traveled. Okay. And what do we get? Anyone got an answer yet? 4.55 meters per second squared. That's our answer to A. B, how much work did gravity do? Maybe that would have been, part A. It could go either way. Work done by gravity, hey, we've already said it's that gravitational parallel times the distance traveled. Now we can't cancel out mass, right? Don't cancel mass here when you're solving for the work or kinetic energy. And so it's that mg sine theta times d so this is kind of after the fact now. I have no clue, but I think it's maybe one that works. So 100 times 4, 400 times sine 15. What do we get? In the hundreds? Did I do something? Huh? Oh, yeah, okay, sorry. 100 times 10 is 1,000. I forgot my 10. So it's 4,000 times sine 15. There we go. Don't forget gravity like me. What do we get? I used 9.8, but I got 1,025. Okay, so with 10, just 1035. And that would be joules. And we already said that it does positive work. So I'm just going to put it there because we can. So there's our answer for part B. Now, what if the kid falls out of the barrel and friction comes into play? Well, to keep it nice, what if they fall an additional 4 meters on their belly and the speed increases by 0.5? Notice that. The speed increases by 0.5. That's a change in speed, right? How much work did friction do? And so for this second half of the ramp, we said we ended at 4.55. Now it's going to increase by 0.5. So my new final velocity would be, yeah, and just because I had a third decimal place, I'm going to keep that. My initial velocity for friction is the final from when I didn't have friction. Okay. So they gave it to us, but you have to do a little thinking there. And the distance traveled is going to be another 4 meters. How much work did friction do now? Okay. So again, same thing, net work. We got gravity minus or plus a negative work done by friction. Hopefully you're okay with me going straight for it, right? Hopefully you know by now friction is going to do negative work. I didn't draw a new diagram, but it would be up the ramp. Gravity, or the object is moving down the ramp, cosine 180, negative. So you don't always have to do the cosine if you just think about it, right? Equals that KE final minus KE initial. And neither zero out if I look at the second half of the ramp. And so work done by gravity, is that going to be the same 1035 or a different number when he falls out? It's going to be the same because they kept the distance the same. So since 4 meters before is equal to 4 meters now, work of gravity is that same 1035. Work of friction is what we're solving for. Kinetic energy, 1/2 mv squared. And so it's the same mass, but now my final speed is that 5.05. Don't forget to square it. And you can factor out the mass. Just make sure you don't mess up the VF squared minus VI squared. Don't subtract and then square. Square, then subtract. All I'm thinking about is the friction burn on his belly, huh? No one gets hurt in physics land. Friction burn by ice. Would you feel heat or would you feel cold? I think initially you'd feel cold, but then
I think you feel pain.
Pain, there we go. Pain. What do we get? Okay. Okay. Yeah, I'll wait for the 10 numbers.
Yeah, I got 7.
Okay. And the SI unit would be joules. And if you're wondering, shouldn't we get a negative answer? Remember, we already said it was negative. So it's tomato, tomato. If you kept it positive, then you would get a negative answer, but you don't want a double negative, okay? Okay, and notice you still speed up, right? You still speed up going down. And so gravity is bigger, doing more work than friction. So it should kind of match what we've said in the past. And then lastly, what is the coefficient of kinetic friction? Well, now we know the work done by friction. And so we can apply that FD. And we can plug in what for the frictional force? Mu Fn. Hey, have we found Fn yet? No. And so be careful here. Is it equal to the weight? Half the students will just say, oh, 500, it's equal to the, or 1,000, it's equal to the weight. On a ramp, you can go back up and look at the diagram. Normal force is balancing the perpendicular component of the weight. And so it's mg, and I'm going to slide up to the diagram, times what function? Cosine, because it's that perpendicular component that's adjacent to the ramp angle in your triangle. Or maybe you took my advice and just memorized those two component equations, right? And so let's go ahead and find Fn. The mass is 100, gravity's 10, cosine 15. Sorry. What do we get? 966. Okay, so 966 rounded. 0.9 is close enough. And so that's our normal force. Now we can go plug everything in and solve for mu. So the work done by friction is that 795 equals mu times the force, 965. Don't forget the distance traveled. Distance is important to the work. And we had what distance during the friction time? 4. That was equal today, but it won't always be equal. First half, second half. And so solve for mu. Again, your check is it should be less than 1.
0.2059.
2059. So we'll say 0.21. Usually they're in 2 decimals. No unit, right? Okay, so hopefully the math is getting boring because we're doing the same thing over and over again, yes? Okay, and so let's do some no numbers. How about that? We end with no numbers. I think on page 5, yes. There's a couple here that don't have any numbers, and I'm going to do number 4 together. Okay, if we have some time, you can try number 3, or you can go and try some more with math. So on page 5, number 4 in the middle, it says a crate of mass m is given an initial velocity of v. So I'm going to start highlighting my variables, m, v, and that's initial. It's allowed to slide across a rough, horizontal, yay, no ramps, floor until it comes to a rest, comes to a stop. So if you want to draw that picture out, maybe the box starts over here. It has a particular velocity, and it's going to slide over some kind of distance, not given yet. And our final position comes to a stop. And it's a rough surface. So what would the diagram be for this object? How big is normal? Here it would be equal to the gravitational force because there's no other vertical forces. And in my picture, they didn't tell us, but in my picture, I said forward was to the right. Friction will act to the left. So who's doing work on this object? Friction. Anybody else? No, because it's moving horizontally, so only horizontal forces do work, or there's not even components, right? And so work is being done. Net work would just be work done by friction. Would it be positive or negative? Negative. Okay, so I haven't even read a question yet. I just kind of got in the mindset of the problem. All right, it says for each of the following modified scenarios, so AP loves to make a change, and it's good science, only make one change at a time. Explain what would happen to the crate's stopping distance. And so it says, in the first change, we're going to double the mass, but everything else remains the same. So what's our answer is, what's happening to this distance, okay, in all of these? And so maybe we actually need to take that equation a step further to get it in distance terms. And later, we'll double the initial velocity. And then later, not necessarily good science, but they still have the right to do it. What if mass doubles and the coefficient of friction, the factor at which the roughness doubles as well? Okay, and so let's keep going with that net work equals the work of friction. Don't forget net work, change in kinetic. We're coming to a stop. So now our final kinetic energy is going to zero out. We come to a stop. And so notice negative kinetic energy equals negative work. Negative is going to go away, right? And so we'll just have that 1/2 mv initial squared equals, and what can we plug in for the work done by friction? Okay, that's a couple steps ahead. So let me at least show one of the steps. So we'll say force of friction times that D. Is everybody okay with me leaving off cosine theta? Because I've already done it verbally. Friction does negative work. It'd be a cosine 180, but I already did the negative and then it canceled out algebraically. And then force of friction here is going to be, they mentioned coefficient later on, but mu Fn times D. And here we already said that Fn is going to balance the weight. And so I can take the right side all the way to mu mg times D. And then bring that left side on down. Okay. So what happens to the distance if we double the mass? Double the mass, it begins with double the kinetic energy, right? Well, mu mg is going to be the same. So how far will it go? Wait, is mu mg? Mu mg would double as well. Wait a second. What happens to your mass? It's going to cancel. So kind of using this as our guide, okay? Mass doubles on both sides. Doubles on both sides. In other words, it's going to cancel. And so it'd be the same stopping distance. All right, reset back to the original. Now, what if you double the initial velocity? How does that affect? So mass still cancels, that's okay. But now we double that initial velocity. How does that affect the distance? If you double the initial velocity, it's going to have more kinetic energy, right? It can go farther, but specifically when you double the initial velocity, don't forget the square. And so I'm going to do this one in terms of the proportion. And so it's not V is proportional to D. It's not a double-double. V squared. So it's a double squared. How far does it go? 4 times the distance when you double the initial speed. Now C is going to get a little trickier because there's a couple changes, okay? And it says go back to the original velocity, V. And so here's where sometimes it's easiest to play the game of 1. Okay, so if everybody starts at 1, then we're going to double the mass and double the coefficient of friction. Okay, and so initially, and I'm going to leave off the 1/2. There's no changes to the 1/2, right? And so we can say, 1 times 1 squared equals 1 times 1 times 1 times 1 mu mgd. I just don't want the 1/2 because 1/2 doesn't equal 1. I'd have to play other games, right? Okay, so now double the mass. So a double on both sides. And the coefficient is going to double, but the velocity stays the same. And their gravity would stay the same. And I know gravity is not 1, but it's just a placeholder there. And so D, what would happen to D? Well, mass is still going to cancel. So really it's that coefficient. But how far is it going to go if you have more friction, a rougher surface at the same speed? It'll go how much less? Half. And so you'd have half the original distance. Half. Good there? I know these problems aren't student favorites, but you got to be ready for it. You got to be practiced for it. AP loves the proportion, okay? All right, next class, we'll keep going with a little bit more practice. I think there was one, at least one on page 6, and then we'll get into the power practice and some of the AP level practice. So no new notes next time, just practice. And we have one more class before the mid-unit quiz, all right? All right, if you want, you can go back and try that one we skipped. You've got a block going down a ramp with no friction, or on page 4, there was a ranking. It had numbers. You can try this one, okay? Don't leave just yet.